Okay, today we really just sort of worked a bit with applications of the Bernoulli equation, trying to illustrate when assumptions can be relaxed, when they need to be looked at carefully, and when they can sometimes surprisingly be violated. Just a reminder, the Bernoulli equation is the statement that this energy group, I introduced that idea today, that we have a pressure potential energy, an elevation, traditional potential energy, and a kinetic energy. Velocity squared, and makes up the kinetic energy term. And the sum of these three terms is conserved under the set of assumptions that I've drawn on the right-hand side here. So for flow along a streamline, so we're tracking an individual particle, when flow is inviscid, to where we're not losing any energy to friction, incompressible flow was necessary in the derivation, and finally, steady flow. If those four conditions are met, then we have energy is conserved along our path along the streamline, and the Bernoulli group is a constant. Now what I tried to do today in lecture was to say, let's talk really about the assumptions behind this and when they can be relaxed. Now one important relaxation comes when flow is irrotational. So irrotational flow is the case where flow does not have any rotation within it. Hence it's called irrotational flow. And we're going to look at this more when we talk about potential flows a bit later. I introduced the vorticity today, the Greek omega vector. When omega is 0, flow is irrotational. In this particular case, so when flow is irrotational, we can apply Bernoulli anywhere. That is, we relax the assumption of the along streamline. So the assumption that flow is along streamline is not required when flow is irrotational. Now when flow is rotational, it's not usually called that, but for illustrative purposes I can use that here. So in rotational flow, when the vorticity vector is not 0, if we want to apply Bernoulli in the cross streamline direction, it has a different form. The cross streamline form of Bernoulli is what we derive for in integrating the Euler equation in a rotating tank. So the cross streamline application would be that P over gamma plus Z minus V squared over 2G is equal to a constant. So that's an alternative to the normal Bernoulli, but specifically here, note we're talking about the cross-streamline application. In any flow, applying along streamlines ends up back at the original form of the Bernoulli equation, which is, I'm just kind of show at the top here, and specifically the along streamline assumption. Finally, we work the example of the submarine as an illustration of when this assumption of steadiness is violated. And specifically in the case of the submarine, so here's my submarine, which is going to be even harder to draw here than on the chalkboard. Moving at velocity v0, flow is steady only in a reference frame moving with the submarine. What that means is that in order to apply the Bernoulli equation, we have to transition into a reference frame that is moving with the submarine in order for the assumption of steady flow to hold. And if we don't do that, we end up with this counterintuitive result that the pressure on the leading edge of the submarine is actually less than the ambient pressure. So hopefully this illustrates to you some of the limitations of the Bernoulli equation and when we can relax some of the assumptions, which is going to be really important as you start to apply it to various problems in the homework and beyond. Have a good long weekend.